Okay, yeah, I'll just kick her off again. So this is Professor Sophia Economou from Virginia Tech, and she's here to tell us about problem-tailored ansatze for efficient variational quantum eigensolvers, which it sounds like a lot of us are very interested in based on the last discussion section. So please take it away.
Thanks a lot for the introduction, and thank you to the organizers for the invitation. It's been a very fun conference, bringing together kind of VQE community, fault-tolerant community, and chemists. So I think it's good to have more of these meetings where there's a mix of people like that. Yeah, so I'll start by acknowledging all my collaborators on these topics, in case I don't have time in the end. So there's 2 graduate students who are very heavily involved in what I'll talk about, several postdocs shown here, and Brian has now left and is at the Georgia Tech Research Institute. And then there's also 2 faculty members from Virginia Tech, Ed Barnes from physics, Nick Mayhall from chemistry, and Nick's student and postdoc were also played a big role in the projects I'll talk about. So I decided to pretty much ditch all my background slides except for 2. So because there's been so many talks before mine talking about background and giving context. So I just wanted to show kind of a slide to remind the difference between analog and digital. And this has also been mentioned in this conference. Of course, we're more interested in digital in this workshop, but there's actually the difference is not as clean cut, at least in the NISQ era, as one would think from the separation. Actually, there's a continuum in between, and you can argue a lot of experiments and a lot of theoretical proposals are kind of treading this space in between. So I think that's another interesting discussion topic. So everything I'll talk about is focused on variational quantum eigensolvers. So you've seen this or versions of this figure quite a bit. So I think by now it's clear what we mean, but just to make this talk self-contained, there is some classical pre-processing step, which I'm skipping here because there's been many talks talking about it before mine, where you obtain a Hamiltonian that lives in the qubit space by doing some transformation from the fermion space so that you preserve the fermionic statistics. And then now you do everything on your qubits. So you create some ansatze, some wave function that's parameterized by parameters that enter inside the unitary, which you're applying on a reference state. And very often we take this reference state to be the Hartree Fock, but you don't have to. And then, of course, you make a measurement, usually of the energy, the mean energy. And then you use your classical computer to optimize in a feedback loop and basically do the variational theorem of quantum mechanics on the hardware. So here's my outline. I'll try to discuss 3 topics within my time. So the first one is on symmetry enforcing circuits. Then I'll talk about adapt VQE. And finally, a newer approach we have introduced called control VQE. So this talk focuses a lot on how do you create a good ansatze for VQEs. And the performance of VQEs is obviously crucially dependent on how good your ansatze choice is. So at the NISQ era, of course, quantum coherence is very limited, which means you would have shallow circuits kind of because that's the reality of things right now. On the other hand, as has been discussed in this workshop as well, classical optimization is far from infinitely powerful, so you don't want to overburden the classical computer. And it goes without saying that you need to span the space where the solution lives. So if you look at the VQE literature, there's probably 2 dominating ansatze. One is the so-called hardware efficient. This is an ad hoc ansatze where you alternate layers of entangling gates. And actually, in its first implementation, this was had an analog flavor, this entangling gate, with single qubit gates, which is where the parameterization comes in, alternating. So this ansatze, it's ad hoc. It's most likely inefficient because you span a lot of the Hilbert space. And there's been this work, and by now much more work that it's too much for me to cite here, so I cited the original paper by Jared, showing that ansatze like this could be too expressive and lead to barren plateaus. On the other hand, there's a UCCSD ansatze, which is taken from quantum chemistry, so you're exponentiating single and double operators, single particle and two particle operators taken from your Hamiltonian terms. And then, of course, you need to translate these into gates. That leads to long trotterized forms. And we have shown that when you stop at early order introtterization, the ordering itself matters, and you might not even be able to get chemical accuracy depending on how you order your operators. So the point I want to make in this talk is that both of these ansatze are generic in the sense that neither of them knows anything about the problem you're trying to solve. So our approach is quite different on this. We are focusing on ansatze that know a lot or as much as possible about the problem we're trying to solve. And we think that by doing that, we should be able to, lead to get more compact ansatze. So this is something we find based on our simulations, more shallow circuits. That leads, of course, to also smaller number of optimization parameters and hopefully exactness. So let me first talk about the first approach we introduced for this, which is symmetry preserving, or maybe symmetry enforcing ansatze is a better word for it. So in a nutshell, you have your Hilbert space shown kind of in a schematic here, H. You have a symmetry subspace inside your Hilbert space, and then the ground state, this is supposed to be a point, but you wouldn't see it if it was just a point. So your ground state is some state inside the symmetry subspace. And here, of course, I'm assuming that you know something about the symmetries of the problem. And the symmetries of the problem can be particle number, which usually is something that's fixed in real problems. But you can also know more about your system. So you can know that there's a well-defined spin or well-defined spin projection, etc. So we use this key ingredient, which was first introduced by the IBM Europe group, which is kind of an obvious choice if you want to preserve particle number in the Jordan-Wigner representation, because here you just mix 0 and 1 with 1 to 0, and you're leaving alone the other particle, total particle subspaces. So the idea is that by doing this, you start from 2 times 2 to the n minus 1 real parameters, which describe an arbitrary state of n qubits, to a smaller space, smaller number of parameters, which is n choose m minus 1 times 2. And this is the structure we have shown that works. So first you use NOT gates, X gates, to fix the total number of particles. So that's fixed up front, and you have a separable state at the stage. And then you stagger these A gates, which mix within this particle subspace, mix enough such that you can span the whole space. And we can count parameters in A and fix the number of A's we need in order to meet those that number of parameters. And we have shown through simulations that indeed we can span any space with 100% fidelity. Basically, we just try states, and we see that we never fail to produce random states within this subspace. And finally, of course, you can also impose time reversal symmetry, which most of these problems have, and limit your parameters even more by a factor of 2 by enforcing that you want real states. Now, there's been some attempts to do something like this before, and we find that if you do a C0 count, which is your currency in the Niskera, you actually perform much better. And then we have also done some noisy simulations on the simulator and hardware of IBM and show that this approach performs pretty well. It performs optimally in terms of the number of parameters, because that's how this is designed. It also performs pretty well, not always better than an ad hoc ansatz in terms of number of CNOTs. All right, so the next thing we want to do is try to see if we can actually zoom in even closer to the ground state or whatever eigenstate you're looking for by, instead of searching inside a subspace, have somehow your algorithm search in a directed way toward that eigenstate. So in kind of a scale of ad hocness of the ansatz versus how tailored the ansatz is, you can think of these hardware efficient ansatz living kind of at the one end, and then the symmetry preserving ansatz is somewhere in the middle, and then the adapt algorithm that I'll talk about is the most problem tailored ansatz, at least that's what we believe. So the key ideas in adapt VQE is that you allow the simulated system to dictate the ansatz, and it is compact by design because it's an iteratively grown ansatz. And to my knowledge, at least, this is the first time an iterative ansatz, iteratively grown ansatz was proposed in the context of VQEs. So this is how the algorithm works. You start with the notion of an operator pool. These are the operators that will be exponentiated to be turned into quantum gates and introduce one parameter each in your ansatz. We'll discuss in a moment how you might select this operator pool. And then what you do is you look at the mean value of the energy, and you see how that is affected if you take the derivative with respect to the parameter that enters in the exponent. And what's nice about that is that this brings down the operator, and you can turn that into a commutator with a Hamiltonian. So you can actually view this step like another measurement. So if you really were serious about doing this on a kind of advanced NISQ platform, then this is a quantum parallelizable step. You would make all these measurements, and then you would see which one has the highest gradient, and you would use that to grow your ansatz. And then you have some convergence criterion here. For example, you could require that all the gradients are 0. In reality, of course, they're not exactly 0, but you want them to be under a certain threshold, and then you would stop. If you don't stop, you add this new operator to your ansatz, you grow your ansatz, and you keep going in this loop until you're converged. And one important point here is that you don't throw away any of these operators. You keep them all inside your pool, even if they're used earlier on. Yeah, I think I already mentioned this. This is maybe for this crowd too detailed. Yeah, so here's the operator pool again. So the question is, how do you choose it? How do different pools perform? The first thing we tried is kind of the most obvious thing. Take a fermionic pool as your pool and run the algorithm. And this is what we did in this paper. So we looked at 3 different kind of small molecules as examples, and we compared UCCSD and then 3 different kind of versions of adapt depending on the gradient selection threshold, the gradient of value threshold. So going to smaller thresholds here should make it more exact. And we plot here dissociation curve. This, of course, at the scale you can't see much, so we looked at the error from the exact solution. And you see that adapt as UCCSD most of the time falls within chemical accuracy, but you can, in the cases where adapt is not in chemical accuracy, which this is the looser criterion, you can just make your criterion tighter and then you hit chemical accuracy. And another thing that's interesting is to ask how many parameters, classical parameters, do you need to do this? So UCCSD is a fixed ansatz, so it has a fixed number of parameters shown with orange here. And then, of course, as you increase the number of times you run your algorithm, which going to smaller epsilon here, you would need more parameters. But you see that the number of parameters is actually much smaller in adapt compared to UCCSD. And one case here where you exceed the number of parameters is where UCCSD didn't manage to find chemical accuracy. Now you could ask, the fact that you are comparing to UCCSD might be a bit unfair because UCCSD, you have all the operators added in the exponent. So you might not be generating effective higher body operators. Whereas when you sort of pseudo-trotterize the way adapt does, maybe that's what's going on. So we tried different orderings of the operators, not the ones adapt predicts, which are shown here according to various criteria, including just random. And you see that adapt seems to do take a qualitatively different path, going much faster to the ground state. And this is one example, but we've tested this thing for many different molecules and bond distances, and it's consistent. All right, so of course, doing, applying to your hardware these exponentiated fermionic operators is still hardware intensive, because each one of these involves many different gates when you trollerize it or when you decompose it. So to avoid that, we asked, can I have a more kind of hardware-friendly pool, which we call a qubit pool, not a very inventive name. And of course, the nice thing about this is that you can choose the pool of operators you have to be kind of conform to your hardware in terms of connectivity and native gates. But in the first kind of test we did, we just took a very simple approach where we took polystrings made up of four terms. And in the simulations I'll show you in a moment, we chose all of them that don't give identically zero derivative. So here's comparing this new qubit pool to the fermionic pool and looking at how many adapt iteration numbers you need, which corresponds to how many optimization parameters you need, because every time I introduce one when I grow my ansatze. And here it appears that the fermionic pool does much better, which it does have fewer parameters compared to the qubit pool. But then, as I mentioned before, an important currency is number of C0s. So if I want to compare now number of C0s, I look here at the blue curve, and you see that the qubit adapt does dramatically better than the fermionic pool. And I should say here, because I get this question whenever I give this talk, that we haven't tried to optimize. We tried actually to give an advantage to the fermionic pool. We didn't try to optimize the choice of qubit pool. We didn't try to transpile. So this is kind of what you get from this first choice of qubit pool, and it performs much better. Now, the chosen pool I showed you is very large, so it has many hundreds of operators, and of course this means many gradient measurements. So one thing you can do is ask, can I actually shrink it? Does it need to be so large? And what we did here is we just randomly started chopping it to a half, a quarter, etc. And you see that at some point you stop being able to converge. This is universal across different molecules we've tried. So this shows you that there's some critical number of operators you need inside your pool, and types of operators you need, and beyond that you cannot chop anymore. So we have introduced the idea of complete pools, which are pools that can take you from any reference state to any other reference state. We're limiting ourselves to real states here, so from any real state to any other real state. And here we introduce the set that's made up of taking your original operators in the pool and taking their commutators and all possible commutators. And then you should be able, if you're able to go from any real state to any other real state by applying these P's, then we call that a complete pool. And we've done intensive numerics to show that this is the case. And here you can see indeed some numerics where how complete versus incomplete pools behave. Complete pools converge, incomplete pools don't always converge. So let me skip this one. Yeah. So the question then we ask is, what's the minimal number of operators in your pool, which we call minimal complete pools. So these are the smallest sized pools that are still complete. And we have a proof in this paper that this number scales linearly with the number of qubits. So this was a very exciting result. And we have examples in the paper that show specific pools, specific examples of minimal complete pools, including a local one. So this only has nearest neighbor terms. All right, so the very last thing I want to talk about briefly before my time is up. I don't know how I'm doing on time.
Should have
10
10 minutes left.
Oh, great. Okay.
life left for questions.
Sure. Yes, that's great. Sure. So even for very kind of vastly simplified ansatze, which can be, are compactified compared to what had been considered before, like adapt VQE, these are still, still long, reasonably, pretty long ansatze compared to what hardware can do. So we thought about kind of going closer to what the hardware can do, and it's been also discussed in this meeting that using pulse level control could actually help, and we call this control VQE. So the idea here is that instead of taking a circuit and parameterizing it in this kind of digital approach that I've been talking about so far, and most people in this conference have been discussing, you could take a pulse and parameterize the pulse directly. So get rid of the notion of a quantum gate altogether. And then do the classical optimization step, similarly to how you do it in digital simulation, to update now the pulse parameters directly. And then you can repeat until convergence. So yeah, this is just the schematic. Nick makes very nice figures. So this is work that was primarily spearheaded by Nick Mayhall's group. And this is kind of a schematic showing this one, that there's parameters corresponding to each piece of the pulse, depending on how you decide to parameterize. So we've done some simulations where we focused on superconducting qubits. We took numbers from transmon qubits of IBM. I don't want to go through all the details here. The important thing is that here, now your simulations will look very different because you need to simulate the time dynamics of the system. So you choose some kind of Hamiltonian. That's your static part, describes the energy levels of the qubits and their interactions. And then you have some control part, and this is the thing you want to actually vary. So the control brings in some variational parameters, which we choose to be the amplitude and the frequency. And then you create your ansatz by doing the time evolution on some reference state, similarly to the way VQEs work. And then you make the measurement and you keep going. So you have, you can optimize your pulse. I'm sorry, you can parameterize your pulse in many different ways. You can take your pulse and chop it kind of infinitely thin if you like, but then you start bringing in probably too many optimization parameters. So you would probably not want to do this for an experimental demonstration. So what we do is we want to keep the pulse length fixed. Again, this is also a coherence kind of consideration enters here. So you can choose your pulse, the total pulse duration, to be as long as you think is long enough to keep your system coherent. And you could start, when you do these simulations, start from kind of short pulses and then grow them as a hyperparameter. And the number of parameters we considered is n plus 1 per qubit. So n is the segment numbers. And we also have one for the frequency. So we're doing the experimentally friendly thing of not asking experimentalists to change the frequency every time the pulse amplitude changes. So let me show you how this would work. You select randomly a point in time where you chop your pulse. So you change the amplitude of your pulse. We looked at square pulses for everything I'll tell you about, but we also have some Gaussian pulse results. And then you do your optimization. So you optimize the parameters of these two pieces. Again, the frequency, you do optimize it, but you enforce it to be constant. And then you keep going. You select randomly out of the biggest piece of the two, and you chop there, and you do the optimization again, and you keep going. So we simulated this on a classical, doing classical simulation. Of course, these are much more computationally intensive because now you're running time dynamics. And for all the examples, we looked at small examples. We always reach FCI, and you can ask how many times do you need to chop your pulse to reach FCI, and you can see for different molecules how the number of segments increases. And it's about 2 for this example, and you reach chemical accuracy with 3, and then you go very close to the real solution here for 5. So you could do a rough comparison of what do you gain by doing this. So if you do gate-based UCCSD, kind of a naive thing, you then translate that into gates, you end up needing 80,000 nanoseconds versus 50 nanoseconds. That is the duration of the pulses we found for these examples. And now that hardware providers are opening up pulse level control, this is probably a very timely thing to start thinking about trying. All right, I also wanted to highlight this paper that talks about quantum control in general and VQEs. I think that's another very interesting kind of direction to think about for the community. Jared is also involved in this paper, as well as my friend Christian Arns. So this is a chemistry conference, and I didn't want to make it about optimization, but I couldn't resist just putting this one last slide before I conclude. And here, I wanted to show you that we have also applied or modified adapt VQE for QAOA, where we keep the QAOA structure, but we use adapt to select mixers. And in all the simulations we've tried, we see that adapt QAOA does much, much better than the original adapt if you allow for entangling gates in your operator pool that's now your mixers. And interestingly, you can get much better performance. You can get it at a lower C0 cost. So this is pretty interesting, and we have a lot of analysis in this paper where we think there's a deep connection with shortcuts to adiabaticity. All right, so this is my summary. I talked about basically 3 things, all of them relating to problem-tailored ansatze, symmetry-preserving circuits, adapt VQE, and control VQE. And you can find the details in these works and these references over here.
Great. Thanks a lot for your presentation. Virtual applause, I guess, is best we can give it. And so does anyone have any questions for Sophia? Looks like Yaroslav is raising his hand.
Yep. Yeah, question. This adapt procedure, it seems a little bit like a gradient descent in the space of gates or in the space of circuits, right? And I was wondering if you try looking at kind of a bit more global optimization kind of things, let's say trying triplets of gates and stuff like that. And a different but kind of similar question is, okay, you tried gradients, you tried estimating gradients, but well, that tells you, let's say, how much energy can you gain. But that actually that doesn't tell you how much energy can you gain. That tells you in which direction you gain kind of locally. And yeah, let's say this basically approximates the landscape with a plane, right? Did you try approximating the landscape with kind of higher order polynomials? That would require calculating higher derivatives for that. And did you try taking that into account? So this kind of global optimization question.
Yeah, thanks for the question. That's a very reasonable, thing to ask, and we have done that a little bit, not enough to give you a satisfactory answer. It's something that we don't have a systematic way of doing entirely. My postdoc, John Van Dyke, who's actually on the call, has tried adding more operators at a time. So I don't know if he has any comments. He's very welcome to unmute and comment. I think I wanted to make one more point related to what you said. Oh yeah, so you also mentioned the gradient as a criterion. We've also tried using how much the energy is lowered as a criterion itself. We didn't find that that's a much better way to go. So far, the algorithm seems to perform very well, at least in, the simulations we can do on the classical computer, that we didn't have enough of an incentive so far to try things that are too much more complicated. One thing we do have in preparation is a more theoretical analysis of when the gradient criterion is actually, formally the right thing to do in order to go toward the ground state. So that's, that's something we're working on. We have a lot of results and hopefully will appear over the next few months.
Yeah, thanks a lot.
Yeah. Any more questions from the audience? Yes, I can ask just a general question. So you have this great adapt technique, and so far, obviously for chemistry, we have some nice fermionic operators to choose from. For near-term applications, there's polys, and now you've added these kind of control operations. Are there any other general pools you're thinking about adding next? Like maybe for some things you'd want dissipative operations, maybe you'd want others, but yeah, I'd be curious to hear what you're thinking about.
Yeah, that's a very interesting question. So we are looking into the idea of dissipative. We have not done it in the adapt, kind of in an adapt way yet, which is something we are thinking about. The way we've done it is by taking, an ancilla set of qubits and doing adapt on the whole system, and then looking at what happens to the subsystem. That's something we are working on. I don't have results to report yet. And another thing I should mention is there's a group in the UK that took our qubit adapt kind of approach and changed the pool, and found that with some other choice of pool, you can actually get a much smaller number of C0s. So if I remember the result correctly, what they found was that you can reduce both the number of C0s and the number of parameters compared to the fermionic pool dramatically. And one of the authors is Crispin Barnes. Unfortunately, I don't remember the first and last author. So if anybody's interested, I think you can easily find it. It's, follow up to the qubit adapt paper. But looking into pools is a whole enterprise. So that's something we haven't done too much, because there's so much more things we want to understand about kind of formal aspects of the algorithm before we try to really optimize, look into optimizing these more detailed features.
Yeah, thanks a lot. That makes sense.